Good morning. As Alex presented me, my name is Alexandre. I work there in IPPT, is the Institute of Fundamental Technological Research. I always forget the acronym. It also belongs to the Polish Academy of Sciences. Maybe you guys didn't heard about it, but it's on the other side of the street, especially because it's full of engineers there. So we are quite isolated in this quantum information and resources group. It's a quite new group there. And today I'm going to talk about certification of quantum states and measurements. Well, maybe many of you went to Antonio Assin's talk last week, I guess. And it's going to be the same topic, okay? But, well, what can I do after Antonio Assin's talk, right? I cannot do better than him. So I decided to do something a bit different. I decided to go to the details regarding certification of quantum states and measurements. So the first part of my talk is going to be very basic, and it is devoted to the students. Okay, I know that here we have many students, and I hope that you guys know basic quantum mechanics, Brass, Katz, and Hilbert space. Do you guys know? Yeah, sure, great. So let's go. What is certification? Well, it's a protocol to verify if the quantum device that you bought, well, not you bought, of course, but the university bought, is working in the way that it should do. So in the label, it says this quantum device has these particles that are maximally entangled, and if you press one button, it does a measurement like this. If you press another button, it does a measurement in another way. How can you be sure that this is actually true without opening the machine? Because one thing that you can do is simply open it and measuring all the devices and all the particles inside, doing a tomography. But the problem is, how are you going to assemble it back again and make the computer work, right? So an alternative way to do that is through a self-testing. A self-testing is a mathematical problem that you give to the quantum device, and the answer is only going to be correct if the quantum device is working in the way that it should work. So it's basically that. It is device independent because it uses only probabilities, and it requires less measurements, fewer measurements, and of course it's less costly. So what is self-testing at the end of the day? You guys know the Born rule, right? If you have measurements and states, you can get the probabilities by calculating the expectation value. So self-testing is kind of the opposite way. So you start with the probabilities, and you want to know something about the measurements and the states from where it came from. And how do you do that? You have to see the maximum violation of Bell inequalities. Let's start with the first example. You guys probably saw this many times, right? Is the Bell scenario. You have two devices, space-like separated, one for Alice, one for Bob. Alice can perform two measurements, these two buttons, these red buttons that I put there, 0 and 1, and she can register two outcomes, plus or minus 1. Same for Bob, okay? So they do this experiment with many particles. You can see that I am a theoretical physicist because I put the drawing of two atoms with orbits there. And after the experiment, after many runs of the experiment, Alice can do a table with measurement choices and measurement outcomes. Same for Bob. They put the two tables together and calculate these probabilities, P of A, B, given X and Y. A, B is Alice's and Bob's outcome, and X and Y is measurement choices. Well, the reasoning says to us that these things should be decomposable into a product, right? Because they are space-like separated. So Alice's results can only come from her measurement choices, and maybe some hidden variable lambda that is in the past of this experiment. could be in the particle itself. Well, same for Bob. And these probabilities that can be decomposed like this, we call them local behaviors. Well, in this, oh, where is my pointer? Do I have a pointer? Ah, I do. I was pressing the wrong button. Sorry, I am a theoretical physicist. So here we have this, this set of all the probabilities that respect this kind of decomposition. We call it a local Bell polytope, or local set, or local correlations. You can choose the name. Well, how self-testing works, you have to see the maximal violation of a Bell inequality. A Bell inequality is a plane that is cutting this set of probability distributions. And if the probability that you have from the experiment violates this inequality, so then your probability is going to be on the other side of the plane, in this side. If does not violate, it is on this side of the plane. So if violates, then you are sure that it's not inside the Bell local set. But if it does not violate, you cannot be sure because it could be, for instance, like this, in this part of the set. Well, when you take all the Bell inequalities from this kind of scenario, you define this set of local behaviors. Okay, what happens if you start violating the Bell inequality, like let's say this Bell inequality more and more? At some point, you have to reach the boundary of the quantum set. And because this boundary is round, it can only be touching only one point. So when you see the maximal violation of the Bell inequality, I'm going to explain the Bell inequality in a few moments. I'm going to show how to derive it. When you reach the boundary, there can be only one point there. And that's why you can do self-testing, because when you see the maximal violation of Bell inequality, it means that that experiment produced only one specific probability distribution, which is that point there. By the way, if you want to interrupt me and ask questions, please do, okay? Even if the question you think that is stupid or something, just ask. Yes?
Is it true that for every Bell inequality you have only one maximizer?
Yeah, I think yes. I'm not sure, actually.
I think you have also the planes that belongs to the local set.
Ah, yes, of course.
In some sense, they are also Bell inequalities, I guess.
Ah, yes. Also, these how do I say, the faces of this local behavior, they are also Bell inequalities. But you can have Bell inequalities that are away from there. Okay, let's take the first example, the CH-SH Bell inequality. So in the same situation, you have Alice and Bob, two inputs, two outputs, two inputs, two outputs. And this is the shape of the Bell inequality. You have four configurations, right? Four measurements that you can do together between Alice and Bob. It's A0, B0, A0, B1, A1, B0, A1, B1. And after you perform this experiment, you can take the expected value doing the sum of the probabilities. And if you use a classical strategy, I mean, if you put only ones and zeros in, ones and minus ones in these expectation values, and you do all the possible configurations that you can imagine, the maximum value is going to be 2. You can think about being 1 for every possible outcome. So you have 1 times 1 plus 1 times 1 plus 1 times 1 minus 1 times 1. That is going to be at most 2. You can think about every other possible combination. The maximum is going to be 2. But sometimes you perform the experiment and you see that this goes beyond that. It can reach 2 square root of 2, which is the maximum quantum value of this expression. How do you get that? Well, one way to get that is to use the state, the maximal entangled state of 2 qubits, phi plus, 0, 0 plus 1, 1 over square root of 2. And the measurements that Alice can perform and Bob can perform to reach this maximum value are x and z for Alice, and also these orthogonal measurements, but 45 degrees rotated for Bob's side. OK, so what is the self-testing in this case? It's a theorem that says that if you reach the maximum violation of this inequality, then there must exist unitary operators that can transform that state that is there in the experiment and the measurements that they are realizing. You can transform them to these zx, z plus x, and z minus x. Well, why that? Well, because these laboratories, they can be tilted, right? You can rotate the laboratory upside down. If you see the violation of the inequality, that means that there are rotations that can bring whatever is there in the system and in the measurement devices to these kind of measurements, if you see the maximum violation of the Bell inequality. OK, so why self-testing we say that is a device-independent certification protocol? It is device-independent. I mean, it does not depend on what is happening inside the box, because it's a black box. You have only inputs and outputs. And from these inputs and outputs, you can get probabilities. Put these probabilities into an inequality. If the inequality is violated, you have something quantum happening. So what are the steps to perform self-testing? You have to choose the states and the measurements that you want to certify. And after that, you have to design an inequality that is going to be maximally violated only by these measurements and these states that you want to certify. After that, you have to use the data from the experiment and put this data in the inequality. If you see the maximal violation, ta-da, you have the certification of the measurements and the states in the lab. So now I'm going to do a crash course on how to design a Bell inequality. This is probably not the most simple way to derive the CHSH Bell inequality, but this is the way that we use to derive more complex inequalities, more complicated ones. We use stabilizers. So let's say that you want to self-test the state 0011. OK? We know that the minimal number of measurements to detect a Bell inequality, or I mean, to detect Bell non-locality, is 2 per party. So Alice does 2 measurements, Bob does 2 measurements. So if you put all the combinations together, you have that expression there. A0 times B0, A0 times B1. Let me put here. Again, I am pressing the wrong button. A1 times B0, A1 times B1. And then you can put some coefficients in front of them. OK? So this is the standard expression. You can go beyond that, but this is the minimum that you can do. So now you can rearrange these terms in a very smart way. OK? You can put A0 here, A1 here, which are the measurement choices for Alice. And you can put together the measurements that Bob are performing, here and here. OK? So put these aside for a moment. Now, you have to look for the stabilizers of the state that you want to certify. What are the stabilizers? These are sets of measurements that can stabilize the state. Well, that does not explain too much, I know. So imagine a measurement, or I mean an operator that you act on this state and you obtain exactly the same state. Pay attention only to this first equation. Well, there are many states that you can put here that will satisfy this equation, right? The phi plus state is one of them. Now, take this second equation here. There are also states that can satisfy this equation. But the only state that can satisfy both of them is the phi plus state. These are the stabilizers of the phi plus state. Phi plus is the 0, 0 plus 1, 1. Okay? Well, now, if you take the sandwich of these two expressions, these two equations here, and you sum them, you get 2. Well, this is the main ingredient to derived Bell inequality. If you put any other state that is not the phi plus state here, one of these two terms is going to be less than 1. Or both of them are going to be less than 1. But the point is, it is only going to be 2, which is the maximum number, if both of them, if you put the phi plus on both of these terms. So this is the main ingredient to create an inequality that is going to be maximally violated only by the state that you want to certify. Is that clear? OK. So now put these two things together. The expression that we have and this equation with the stabilizers. Do you see some resemblance between them? They have a sum of two terms. They are products. OK? So then we can fix Alice's measurements to be this z here and this x here. And Bob's measurements, they have to be such that when you put them together, you have z and x also. What are going to be these measurements? I don't know. It doesn't matter. What matters is that I have to construct something that is going to be that is going to reach the maximum value when you do the right choice of the measurements. So then you have to solve these equations. Some conditions that you have to impose. For instance, a squared plus b squared needs to be equal to 1. You have to put some considerations. And then one of the possible results for a, b, c, and d is 1 over square root of 2 and minus 1 square root of 2. If you put them together, then the measurements that will give the maximum violation for phi plus, they need to satisfy this relation here and this one. So here are the ingredients for your Bell inequality. Is the sum of this term and the sum of this term. Where is the square root of 2? Doesn't matter. Why? Why? Because this term is multiplying everybody. So it's going to be a global term that it will only increase or decrease the maximal value of your inequality. But that doesn't matter. So this is your Bell operator. It's not the Bell inequality yet. You have to take the expectation value. So now we have to calculate the classical bound and the quantum bound. What can be reached classically and what can be maximally reached quantumly. To calculate the classical bound, you can use brute force. Sometimes it's quite hard to do it analytically. Most of the time, it's quite hard to find it analytically. So we do simply by trying all the possible combinations. So you put there plus 1 times plus 1 minus plus 1 times plus 1, and you go. Then you see that the maximal value, classically, is going to be 2. Now, the quantum bound. Usually, you can do it analytically by using a sum of squared decomposition. Well, the sum of squares seems to be something that I just took out from the hat, right? But there are ways to obtain it with NPA hierarchy, or you can use your experience from looking at what have been done in the past. So it's an intelligent way, it's a smart way to decompose your Bell operator in terms of terms that are going to be squared and summed. So this needs to be greater or equal than 0. So if you do the math for these guys here, you are going to reach 4 times identity minus square root of 2 times the Bell operator. Well, if this thing here is greater or equal than 0, then you can solve the equation, take the expected value, and this is going to be less or equal than 2 square root of 2. This is the quantum bound. So this quantum bound is going to be achieved only when you have the state as phi plus And the measurements that Alice and Bob are performing need to be these ones. And this is your Bell inequality.
Up to local unit.
Up to local unitaries. Now, if the maximum violation is observed, then there must exist local unitaries that when you apply to the state, is going to give you the phi plus state, and the measurements need to give you z, x for Alice, and z plus x, and z minus x for Bob. Well, how do you prove that these unitary exists? There are some ways to do that analytically. But there are other ways where you simply show one unitary that does that. For instance, this one. Well, this unitary, you are not going to apply in the lab. You don't need to do that. But it's just to show that there exist local unitaries that will transform the measurements that Alice and Bob are performing and the state that they have into the state that you want to certify and the measurements that you want to certify. So if the maximal violation of the inequality is found. OK, so that was a big introduction. From now on, I'm going to talk about the stuff that we did in the last year, maybe 2 years. What was already self-tested? Any pure bipartite state and any pure multipartite state. These are results from Coladangelo and Shupich. And when it comes to measurements, then things become more trickier. We know that we can self-test measurements that are based on mutually unbiased basis. Also, some classes of composite measurements. And one very important result that we had last year from the group of Laura Manchinska, is this one that is called all real local rank 1 projective measurements can be self-tested. Well, but that result requires that you need to do d to the 3 number of measurements, which is a lot of measurements. It is more like a proof of principle result. It doesn't mean that it's practical to do in the lab, but it is mathematically possible. So what is there to be done? What we can do from now on is to design protocols that are simpler, that uses less measurements. And also, you want to certify more complicated situations, with more parties or more dimensions. So what we did so far, we have a universal scheme to self-test any quantum state and measurement. We have another one that is called almost device-independent certification of GME states with minimal number of measurements. And we also, the last one that we had is certifying classes of D outcome measurements with quantum steering. How much time do I have, by the way?
Wait, until 12 or 12:15 max.
12 or 12:15. OK, yeah. I think we will have time to. OK. Plus questions. OK, let's see where we can go. All right, I am not planning to show everything. Let's see where we can go. So just a quick review. When I talk about measurements, I will talk about 3 classes. So POVMs, projective measurements, and extremal POVMs. Are you guys aware of these 3 classes? I guess that POVMs and projective measurements for sure. Extremal POVMs. Extremal POVMs are POVMs that cannot be written as linear combinations of other POVMs. It's just that. One example of extremal POVMs are SIC POVMs, symmetrically information complete measurements. OK? So if you want to see more details on this, I suggest a very nice paper from Teiko Renosari on quantum information processing, where they show that you can write every finite outcome POVM as a function of rank 1 extremal POVMs. You just need to do relabelings and mixings. Okay, so we want to self-test extremal POVMs, rank 1 extremal POVMs. Suppose that we have all the resources that we can do, okay, that we can obtain. As many parties as you want, as many measurements that you want to do, but we want to do it device independently, only with probabilities. I know that rank 1 extremal POVMs are quite big classes of measurements, right? So one way that we found to do this is through this network. So put this extremal POVM in the second choice of this device that is controlled by Eve. So Eve can do 2 measurements, and one of them, the second one, is going to be our measurement that we want to certify, this rank 1 extremal POVM. And outside, we have many Alices. Okay? And each one of these Alices can perform 3 measurements with 2 outcomes. And they share these bipartite states. Okay? I know that it sounds like super complicated, but this is a proof of principle. We want to check if you can self-test extremal POVMs. Well, how many Alices do you need? You need a number n of Alices such that 2 to the n is greater or equal than the dimension of the POVM. So if the dimension is 2, you need only 1 Alice. If the dimension is 3, if you are working with Q-treats, then you need 2 Alices. Because 2 to the 2 is 4, 4 is bigger than 3. Okay? So how do we do that? Well, first, you have to perform the experiment. So everybody press buttons, they register outcomes. Okay? And at the end of the day, you compiled everything. And then you select only the data that comes from when Eve presses 0. Okay? And then this data needs to violate this set of huge inequalities that I have here.
So 0 is some reference measurement, yes?
Some reference measurement, yes. And then, if all these inequalities are maximally violated, it means that we can self-test that. First, the 3 measurements that the Alices are performing are those ones, x plus z, x minus z, and y. And for all the other Alices is going to be z, x, and y. The source is producing 5 plus states, the qubits, pairs of 2 qubits, maximally entangled. And the first measurement that Eve is performed is the measurement that comes from the G8Z basis. Okay? So you see, I took part of the data to self-test part of the network. Now that I know that this is true, now that I already know that this part is self-tested, I know the states, I know the first measurement of Eve, then to self-test the extremal POVM that you want, what you do is you decompose this POVM in Pauli basis with that expression. Then you have to find what is going to be this coefficients f here. So this is the POVM that you want to certify. You have to decompose it in the Pauli basis. You have to find what are these coefficients. And then we derived one kind of constraint that needs to be satisfied. That comes from those coefficients of the decomposition of the measurement that you want to certify. So if these constraints here are satisfied, then it means that there must exist unitaries that will transform that measurement that is happening in the lab to the measurement that you want to certify. Same procedure for extremal POVMs. What is important that the measurements need to be extremal POVMs because they cannot be written as linear combinations of other measurements. So then these coefficients f, they're going to be unique. There is a unique decomposition. Okay, this method is super complicated, right? Because you have to do a lot of measurements, and you have to use many parties. How do we reduce the number of measurements that we can do? One of the ways to do that is to trust one of the parties. And that is called semi-device independent self-testing. So you trust one part of your network. You already assume what are the measurements that they are doing. And then your inequality is going to be simpler. In some papers, we can prove that the number of measurements that you need to perform this is going to be only 2. So you can do only 2 measurements in each party.
Down from V to the third. Or is it no?
No. There is no relation between
Okay.
between them. I know it sounded like that, but no.
Sorry.
No, that is okay. So what we are using in this case, well, then is not Bell-known locality, is steering. So in steering, your local hidden variable model that is written like this product of probabilities, you see? One of them, you assume already that is coming from some quantum measurement. So instead of putting a probability here that comes from something that you don't know, you trust the device, and the probability comes from a measurement, a quantum measurement. So let's see what we can do with genuinely multipartite entangled states. You have many particles that are genuinely multipartite entangled. If you trust one of the parties, let's say Alice, and you don't trust any other party, then we can reduce the number of measurements to only 2. And then we derive an inequality and see the maximal violation of that. Just to remember what are GME states, where these are the states that you cannot decompose as a product in any possible way. Okay? We self-tested 3 classes of GME states: multipartite Schmidt states, generalized W states, and graph states. Well, given the time that I have, I think I will focus only on multipartite Schmidt states. So we know that every pure bipartite state admits a Schmidt decomposition, right? You can write it as simply I times I. And if you go to more particles, that is not necessarily true. You cannot write every multipartite entangled state as a Schmidt decomposition. Well, but there are some states that you can do that. And these states that you can do that, we call multipartite Schmidt states. They have this shape here. So now you see we have many parties. The states are d-dimensional. And we want to self-test this kind of measurement. What is going to be the inequality? And what is going to be the measurements that you need to perform? The state. Well, to do that, we can use one method for higher dimensions that is called generalized Pauli matrices. Well, you guys know the Pauli matrices in 2 dimensions. But then you can go to more dimensions if you use complex eigenvalues. So for Z and X, you can write the generalized Pauli matrices as omega to the k, where omega is this complex number in the circle of the polar plane, of the complex plane. So for d equal 3, what you have is 3 complex numbers in this circle of distance 1, okay, that are equally spaced. So omega to the 0 is 1. Omega to 1 is up there. And if you square it, omega squared, then you have down here. You can keep multiplying it, and then you simply rotate. Well, your Z matrix is going to have this expression, 1 omega, omega squared. It is the analogy of sigma Z, right? Because in sigma Z, you have 1 and minus 1, right? So if you go to higher dimensions, you can use complex numbers to take these eigenvalues as outputs. Well, but then how do you do that in the lab, right? Because these are complex eigenvalues. Well, then we have to work with generalized correlators. So we know that the probabilities are written in that way, right? Trace of the operators applied to the state. You can do the Fourier transform of these probabilities and work with these generalized correlators. And then your measurements now, A and B, they are going to be given the expected value of that is going to be given by the Fourier transform of your probability. And then when you do that, you gain some properties, some, how do I say, mathematical tricks to deal with higher dimensions. So the steering operator that we are going to use for that has this shape. You have to put all the measurements together. This expression comes from previous expressions. We can calculate the classical bound. We can calculate the quantum bound. And then at the end of the day, you can show that if you see the maximal violation of that inequality, then the state that you have is unitarily, local unitarily equivalent to the multipartite Schmidt state. And also the measurements that Bob is performing, all the Bobs are performing, they are equivalent to Z and X. OK, should I go to these guys? Maybe not. I think I'm going to pass this. Yes?
If you have access to Alice, is it not obvious that straight away you know the dimension? Because if I have a GME, is it not very strong? Because Alice opened the box, she already knows that I is sum from 1 to D. So some kind of, you are kind of certifying GMEs of dimension D, no? And this you know straight away.
Yes. That's why you can reduce the number of measurements. OK, so now classes of D outcome measurement. OK, so we know that for dimension 2, you can write a linear combination between Z and X. Okay, you take Z and X. There are constants that you can put there, alpha and beta. It doesn't matter. You can find it as a unitary operator. And if you go to higher dimensions, there is no way that you can put a linear combination between Z and X only that is going to be unitary. That cannot be done. But to make it unitary, you can add all these operators from the Heisenberg-Weil basis, X times Z squared, until D minus 1. And that is unitary. So in this paper, we show that we can self-test this kind of measurements as a function of these constants. How do we do that? Using only two parties. But then we have to use D measurements on each side. How do we do? We use the same method before. We have the stabilizers. You guys remember that the stabilizer of the phi plus the state is only Z times Z, X times X. Well, if you go to higher dimensions, then the stabilizers are going to be this set of measurements. They look a bit ugly, I know. But you can use them to derive steering inequalities. And then we can calculate the quantum bound, classical bound in the same way, using sum of square decomposition. And then if you see the maximal violation of the inequality, you know that the measurements that Alice are going to perform are going to be this, and Bob is going to perform this kind of measurements. Well, for dimension 3, for Q treats, if you fix Alice's measurements as xz to the minus 1 and xz to the minus 2, then Bob's measurements can be written as a linear combination of those measurements. And depending on the coefficients that you choose, you have different classical bounds. So we can certify all these class of measurements with different classical bounds. But for dimension 3, the quantum bound is going to be, in this case, 6, if I am not wrong. Yeah? the quantum bound is sick. As you see, some regions are quite red, so they are very close to the quantum bound. Remember, this is the classical bound. So in these regions, you cannot self-test the measurement, right? Because the classical bound is equal to the quantum bound, so the inequality is useless. So I think I can finish here. Just to summarize. So to self-test multipartite states, you can use device independent, then the networks are going to have a lot of measurements. Semi-device independent way, then you can use networks and that will reduce the number of measurements. And to self-test higher dimensional states, then you can use generalized Pauli matrices. I think this is the summary that you can have of this talk. Thank you very much.
Yeah, thanks, Alexandre. Do we have questions?
Very quick one, but I think you just, because you said steering inequality, the last part was non-locality. So this is not the steering inequality. Here everything is at the level of probabilities. Here you don't open the boxes.
No, here I trust Alice's site.
So it's also steering, okay.
This is also string. No, this case I trust Alice's site.
So maybe I ask a nasty question because you started with quantum computer example that we need to certify that it works properly. So what is the path from what you said to certifying quantum computers?
The inequality is the mathematical problem that you give to the quantum computer so it can solve it. And by solving, I mean reaching the maximal violation of the inequality.
So you would what? So, okay, so I give you this processor, and I want you to tell me if it's a perfect quantum computer.
Yes.
So then what you do?
You press the buttons. Well, you need to choose.
I mean, you try to prepare the state.
Yes.
Yes. Or you because so you would use this certification for the state.
Also for the measurements. I showed only how to certify the states, but you can also do that for the measurements.
Okay, but on the other hand, if I want to certify the transformation that it does, then I should what? Use entangled state with some ancillary systems or what? I mean, because I want to understand, okay, you do something and tell me, okay, this is real quantum computer that does this quantum gates.
Mm-hmm.
Okay, and it's exactly this process. So I think you need to entangle that with ancillas, no?
So you want to self-test the operations that is going to make.
Yeah, because this is a certifying quantum computer, yeah?
Yeah.
Say, no?
Well, then you need to self-test the maps, I guess.
Mm-hmm. Yes. So
And there are procedures for that.
But it's just entangling with ancilla and certain states or something different?
I'm sorry that I cannot.
I mean, I think, at least from my basic knowledge, is if you have this CHSH inequality and you somehow really reach this 2 square root of 2, then, I mean, as you said, no, then you are sure that somewhere your devices are doing sigma x and sigma z with some, maybe in some different bases, right? So then, like, you can be sure that at least this is happening, right? But okay, you don't know.
I think what he means is the operations that the quantum computer is going to do in a big network, right? You have an algorithm full of.
You want to self-test at least the single bit. Because that is not enough, but single bit, something entangled.
Yeah, I don't know. Probably there is a way to do that also. No? Okay, any other questions? Maybe I have a question. So
Yes.
I think you didn't mention that here, but I know. I mean, I heard that. Okay, because let's say CHSH inequality, so if you are sure that you reach this 2 square root of 2, then you're sure that somewhere you have a Bell state and some sigma x, sigma z measurements. But like in practice, you will never be sure that you have exactly 2 square root of 2. No, you will have maybe 2 square root of 2 minus some delta, yes. Mm-hmm. So is that also known, like how, I think it's, yeah. Is it also known?
Yes, sure. It is known, and it's something that every referee is going to ask.
I know. Okay.
is the proof of the robustness.
Mhm.
So basically what we have to do is to say, okay, if there is an epsilon that is separating you from the maximal value of the inequality, then how close are you going to be of the measurements and the states? So it's just a epsilon delta relation that you have to find. So the closer you are from the maximal quantum value, the closer you are to the states that you want to certify.
But this is all known only for CHSH, right? Not in general, right? So for
No,
this,
we do
for those things
robustness
that
for many procedures, yes.
So for those things that you also did, this is also analyzed.
In these ones that I presented, no.
Oh, and another thing. I mean, okay, let's say with the CHSH because it's very simple. So from my naive knowledge, this 2 square root of 2 violation, you kind of assume that that the source is giving you the same state every time, and I think you also assume that your measurements don't have a memory. So is there anything known, let's say, about the CHSH inequality if I also assume that my measurement devices, maybe they remember all measurements that have been done, and also that maybe that the source can send me also like some states which are even entangled across different realizations. So is it also known whether from being close to 2 square root of 2 I can say that I essentially have a Bell state in every round or in most rounds? Something like this. Do you know?
No, I don't know. Maybe the inequality needs to be adapted for that.
I vaguely remember there was something, but yeah, I think it's a bit, yeah, okay. Too specific for this talk. Okay, thanks. Thank you. Anything else? No? So we don't have questions from students, but okay.
Was it too much? No, was basic.
I think it was, yeah, I think good
Okay.
for broad audience. Okay, thanks again.